Hey, what's up? How's the sound here? Cool. Sounds pretty good. Let's see. Twitch is maybe working? Twitch. Alright. Internet is going, or went down for a second. Is it back? Is it not back? Alright. I think everything's back now. Okay, yeah, so I was gonna basically keep going through the paper here tonight and see how far we get. This probably will be my probably be a little bit of a shorter stream, like maybe only an hour this time. And then two, I think I am going to go through this for this evening, and then wherever I get to is probably where I'll stop. Like I think the prereqs for this paper are a little bit out of my wheelhouse, so I could go down the rabbit hole reading, for instance, this paper looked like it was a good summary. It's of course pretty long, 80 pages long, but this could be something I come back to. I'm still kind of playing with the idea of what to stream while I'm kind of waiting to build an audience to do like the homework help stuff, which is like what I really want to do on this channel. But yeah, I think reading papers might not be a bad. Alright, man, my internet is really killing me tonight, so hopefully this doesn't end up being too much of an issue. But already is not going great as far as the network goes. I'm not sure if it's like my internet or if it's this restream service that I'm using. Yeah. I don't know. I guess it's my internet because it says OB. No, that's not necessarily true. Anyway, let's just get to the physics here. So, last thing we were reading was they were starting to actually get into the circuit. I think we were like kind of at the top of this page. Right, so let's just start from this sentence. So they perform the following benchmarks for establishing an eigenstate ordered non-equilibrium phase of matter. One, they change the drive parameters to demonstrate the stability, that the phase is stable in an extended parameter region. And they say that this addresses the fact that the network is of finite size and has finite coherence time. So by varying the number of qubits in the system and by separating effects of extrinsic decoherence and intrinsic thermalization. They're saying that so they say finite size basically is addressed by varying the number of qubits, and finite coherence time is addressed by separating the effects of intrinsic thermalization and extrinsic decoherence. The existence of eigenstate order across the entire spectrum is established. The flexibility of our quantum processor, combined with the scalable experiment protocols devised in the following, allow us to fulfill these criteria and observe time crystalline eigenstate order. The experiment is conducted on an open-ended linear chain of length L equals 20 qubits, superconducting qubits. These are isolated from a two-dimensional grid. I think, yeah, we talked about this yesterday. They probably mean on a two-dimensional grid here. We drive the bits via a time periodic circuit with t identical cycles of this operator UF, which is defined here, and is a rotation about x. This correlation between the two nearest neighbors, and then a rotation about z. Where x and z are Pauli operators, which just means that their action is to rotate the state along those axes, rotate the spin of the state, and since these are presumably spin qubits, transmon qubits. I mean, yeah, this is always what it means. I mean, you can always think of it as spin, even if it's not actual spin. So each phi I, or each phi I hi, or hi, I guess they mean. So phi is the amount that they, so I guess, I mean, this is some sort of rotation as well. Any operator in quantum mechanics is going to be some sort of rotation. I'm not sure if there's a obvious interpretation of what this rotation is when you're doing the pair of so like I guess what this really does is it introduces the particles next to each other or something. Yeah, I wonder how they actually do this, because like this would be a this is an interaction between the spins, spin-spin interaction. So I guess that just means, yeah, they bring the particles together, but would XX be different than ZZ? That I'm not sure about. I guess they must all be the same somehow. Anyway, so there's some, if you think about it like as a single particle, they basically apply a magnetic field along the x-axis, then they bring the two qubits near each other, and then they bring the other two qubits near each other, the two that are close together with the next two that are close together, and they apply a magnetic field along the z-axis. And the amount of time that they let these two spins interact with each other is phi I, and the amount of time that they apply this z field is hi. And they're saying, I guess, that those are random numbers or something. I'm not sure why that would be the case or why that's necessary. But anyway, each phi hi is sampled randomly from minus 1.5 pi to minus half pi for phi, and from minus pi to pi for h. For every realization of the circuit. Overall, UF implements an interacting icing model that is periodically kicked by a transverse pulse that rotates all qubits by pi g about the x-axis. Okay. So they're saying like these are like the natural, I guess they're saying there's like always a z field, and this is kind of the natural interaction of the particles of the qubits with each other, and then they're interpreting these x's as being like pulsed. I'm not sure if this is just an interpretation thing or if there's something else going on here, because this is like technically being pulsed too, and so is this in this paradigm. but yeah, it's interesting. Determines pulse that rotates all qubits by pi g in the x-axis. Right. G. Right, this one. Yep. In this work, G is tuned within the range 0.5 to 1 to explore the discrete time crystal phase and its transition into thermal phase. In this work, G is tuned here to explore the transition between the thermal phase and the time crystal phase. At G equals 1, the model implements a pi pulse, which exactly flips all qubits in the Z basis and returns them to the initial state over 2 periods. At G equals 1, G is in front of X. Okay, I buy that. So this operator here acts to flip a qubit in the Z basis at least, and returns them to the initial state over 2 periods. I guess they're just saying 2 flips brings you back, of course, to the original thing. Peak signature of the discrete time crystal is the presence of robust period doubling, i.e. extending over a finite extent in parameter space, even as G is tuned away from 1. Strong icing, so I guess they're saying even if G isn't 1, somehow you still get this flipping. Strong icing interactions which produce long-range spatial order are essential for their robustness. This is in contrast to a system of decoupled qubits in which phi would equal 0, which rotate continuously, varying angle pi g every period instead of being locked to period doubling. Interesting. So I guess they're saying if this term wasn't here, if there wasn't the interaction between the qubits, if I change G, then I'm not going to get the particles flipping every time. But if I have this term, then even if G is not 1, this circuit still acts to flip it. It's interesting. Prior theoretical work has shown that the model 1 is expected to be an MBL DTC phase in the range G greater than GC and transitions into a thermal phase at a critical value of GC equals 0.84. This paper might also be good. Number 32, what we got there? 32. Many-body physics in the NISQ area, quantum programming, something. Let's grab this. Matteo Ippoliti. I haven't heard of any of these people. Stanford, Google, Max Planck, Princeton. Neat. That looks fun too. Okay. Achieving the many-body localized. The achieving many-body localization in this model for G is about 1, requires disorder in 2-qubit interactions phi I, which is even under Ising symmetry. The product of all x this is an Ising symmetry they're saying. Yeah, I'm pretty sure I should probably just double check this. I'm pretty sure x essentially acts by flipping every spin. Right. That's really weird that this model causes the, if what I'm thinking is right, that it actually flips everything back and forth. Like this is, I guess they probably show that in this paper. Okay, so achieving the many-body localization in this model for G approximately 1, I guess is what they mean here, requires disorder in the 2-qubit interaction phi I, which is even under Ising symmetry, a condition that is not met by some past DTC experiments. Ising odd terms here, i.e. HI, are approximately dynamically decoupled by x pulses over 2 periods. Approximately dynamically decoupled, thereby lowering their effective disorder strength and hindering localization in the absence of an independent disorder in phi I. Are approximately dynamically decoupled from the x pulses over 2 periods, thereby lowering their effective disorder strength and hindering localization. Okay. Utilizing newly developed C-phase gates with continuously tunable conditional phases allows us to engineer strong disorder phi I to fulfill this key requirement. Okay. Interesting. I'm not sure what strong disorder is, but I guess they're saying something is very special about this phi parameter that makes this thing work. Like maybe there's some distribution it has to be drawn from or something. That's what I'm guessing. We first measure the hallmark of the many-body localized discrete time crystal, the persistent oscillation of local qubit polarizations at a period twice of UF, irrespective of the original state. This subharmonic response is probed using a collection of random bit strings, where 0 or 1 denotes the single qubit, and the Z basis. For each bit string state, we generate a random instance of UF and then measure. Okay, so what are they saying they're doing here? This is actually kind of the meat of it, it seems. So they're saying that like the main thing that they're looking to see here is that no matter what initial state the qubits are in, if you apply this UF over and over and over again, that I'm not sure what this measurement is, expectation value of ZT. But this expectation value of ZT is going to be a function that oscillates in t at twice the period of UF. The subharmonic response is probed by using a collection of random bit string states. So they basically choose a random state for the qubit. For each initial state, they generate some random instance of UF and then measure Z of t every cycle. Figure 2b shows Z of t in quite a few different instances for a qubit near the center of the chain. Q11 is measured, the 11th qubit. Figure 2b, is this 2b? No, this is 3. 2b, this. Okay. Experimental values of ZT measured at qubit 11. Data are shown for 5 representative circuit instances in the deep thermal, G equals 0.6, and MEL-DTC phases 0.97. Interesting. Okay, so what you're looking at here is they basically measure the spin, the Z spin of the qubit, or whatever that Z spin represents in this actual instance of a qubit. They measure that every cycle that they apply this operator to the qubits. And then on the left here, the pulse of X magnetic field onto the qubits is not that long. It's not that long. It's long enough to spin the qubits by about 60% of a 180-degree turn. And they see that when they do that when they measure the Z spin after each cycle, you get this really fast decay of the Z spin, and then ultimately you get total disorder. So this is the expectation value of Z. This means that like when it's 0, it basically means that you're just as likely to get spin up as spin down in the Z basis. But when you increase that magnetic field, the time that you expose that system to a magnetic field in the x direction, you can see that the expectation value of Z, basically you get Z flipping so that the Z spin, at time 0 is like basically guaranteed to be 1, and then at time 1 is guaranteed to be -1. So like after one thing, presumably I'm assuming that T is each cycle. Yes, it's T cycles. So yeah, basically you can see that you just keep getting this thing flipping. The one thing that I'm interested in seeing here is like, I kind of wish I could see how close these dots are together. Like, does it look like, yeah, it's too hard to count how many dots there are in here. But like, are they making a measurement at each after each cycle? Because isn't this thing supposed to oscillate at twice the cycle frequency? So like if you want to see this oscillation, shouldn't we actually have to measure Z like inside of the circuit? Or maybe they're saying they let some like time pass between successive instances of applying UF or something. Interesting. All right, but let's keep going. So figure 2 shows expectation value of Z in a few different instances for a qubit near the center of the chain, which is number 11, at 2 different Gs. The former is deep in the thermal phase, and we observe a rapid decay of ZT towards 0 within 10 cycles for each instance. In contrast, at the high G, shows a large period double oscillation persisting over 100 cycles, suggestive of an MBL DTC phase. The disorder averaged autocorrelator. So they're defining this as the disorder average autocorrelator, which is the expectation value of Z at time 0 versus time t. Shows a similar feature in 2C. Yeah, so I mean this is just normalizing it so that the initial, basically the initial value is always it's like kind of the same curve here, but they always set the initial value of, so see how like these have kind of like different heights, and also some of these will start up here while some of them start up here because they randomize the initial state of the qubit. So this basically just like enforces that they always start up here, and the height is like relative to the initial height, I guess. Not totally sure. Not totally sure about the second one. Okay, so we note that the data for G is 0.97 is modulated by a gradually decaying envelope, which may arise either from external decoherence or from slow internal thermalization. Number 30 and number 25. What do we got down here? I'd really like to learn more about just like what thermalization means. I'm like, that's, like I said, one of those things that's always kind of confused me. 25 and 30, right? So 30 is critical time crystals in dipolar systems. Okay. Observation of discrete time crystalline in disordered dipolar many-body systems. Okay, this one seems like another experiment paper, which maybe doesn't have the best explanation. Perhaps this will be the easier to understand one. Is this open access? Nope. Is it on archive? It is. University of Geneva. Nice. This also seems like a good paper. Okay. Okay, so to establish a discrete time crystal, additional measurements are needed to distinguish between these two mechanisms. This is achieved via an echo circuit, which is UF dagger to the T. Oh yeah, so at t times, fine. Uf to the t, which reverses the time evolution after t steps. Okay, so they're just saying they apply this same circuit like t times, and then they, in the opposite order. I'm not sure if they're applying, if they're again randomly selecting these phi and h, or if they're in the or if they're kind of like nested, like the phi and h they use for the first one in normal direction is like the same phi and h they use for the first one in the opposite direction or something. I'm not sure about that. Deviations of u echo, but basically they just say that they can apply this operator instead. Which is going to distinguish between decoherence and thermalization. Okay, so deviations of u echo from identity operation are purely due to decoherence and can be quantified via decay of the auto. Okay, so yeah, so they are nesting. They are using the same phi and h values because this is ultimately, if you evolve it one way and then de-evolve it with the same values, then you should get the same state again. But they're saying that when you do this, you don't actually get the same state again, and they're saying that that is totally due to decoherence, and I buy that. They're just saying that that's not part of the decoherence. Just means like interactions with the external environment, basically. The Poltrix. What's time crystal? So time crystal is could mean a lot of things, but in this paper, they're talking about basically a quantum system that has some kind of like repeatable. So actually, I'm definitely not the greatest person in the world to ask about this, but the basic idea, as far as I understand it, is it's like a system that will essentially like end up back in the same place that it started. So like a normal crystal, what we mean is like when you have something like ice, you like can, if you were like shrunk down inside of the ice crystal, you would see little molecules of like hydrogen and oxygen everywhere. You'd see all these water molecules, right? And I think ice is a square lattice. So like if you like shrunk down, you could sit inside of one of those squares that there's all those water molecules around you. And if you move around in space, if you're inside of the ice cube, you'd basically end up back inside of these little squares. So there's this like repeating pattern, throughout space. And that's like a regular crystal. So it's a crystal in space. So a time crystal is the same thing, but instead of being able to move around in space and seeing the same configuration around you, you'll move around in time and you get back to the same configuration. So that's the basic idea behind the time crystal. Kind of like a system that's periodic in time. Okay. So where are we at? Right, from U echo, the identity operations are purely due to decoherence and can be quantified via decay of the autocorrelator. Z, then U echo bar, then Z, then U echo. Via decay of the autocorrelator. Square root accounts for the fact that U echo acts twice as long as the regular UT of F. I think this just means that you can, let's see, a figure for this somewhere. I think this is basically just measuring the size of the z spin after applying this U echo, and then applying the inverse operation and checking the z spin again is what this thing means. And then multiplying those two values together. Something like that. Yeah. Okay, a similar time reversal technique was recently used to study out-of-time disordered commutators in thermalizing random circuits. Comparison between the disorder average, a 0 bar, which I guess is this thing, okay, and a bar, which is this thing, reveals qualitatively different behaviors for the two phases in figure 2c. Let's see figure 2c. What does A0 mean again? So they apply a bunch of these. Which should have eigenvalue 1. And they apply this z. Then they apply a bunch of the same thing in reverse, which again should have eigenvalue 1. Or minus 1. Or I guess has to be 1. And then apply the z measurement again. Let me just check something about eigenvalues here. What if we just go symmetric first? I don't think the okay eigenvalue. Yeah, it's definitely they have the same eigenvalues if they commute, but I'm 90% sure that I mean these things do not commute because x and z don't commute, and this thing has an x in it. Um, okay, it's gonna keep moving. In the thermal phase, a bar approaches 0 much more quickly than a 0 bar does, indicating that the observed decay of A is mostly introduced by intrinsic thermalization. In the MBL-DTC phase, A0 nearly coincides with the envelope of A, suggesting that the decay of the latter is primarily induced by decoherence. Seems like this is a word that they mainly use themselves. What happened to the PDF here? I'm not sure where that downloaded to. Alright. So they're saying that in here, you see that this correlator decays like right away, whereas this thing takes a long time to decay. And they're saying that means that this thing, or that's because this thing is only sensitive to intrinsic thermalization, whereas this thing is sensitive to decoherence. And so they're saying this thing is only sensitive to intrinsic thermalization is what they're saying. Okay. Why would that be the case? Number 33. This might be a pretty subtle point. Information scrambling in computationally complex quantum circuits. Interaction quantum physics can spread initially localized quantum information into many degrees of freedom in the entire system. Understanding this process of quantum scrambling is the key to resolve various conundrums of physics. Here, by measuring time-dependent evolutions and fluctuations of out-of-time order correlators, we experimentally investigate dynamics of quantum scrambling on a 53-qubit quantum processor. We engineer quantum circuits that distinguish two mechanisms associated with quantum scrambling. Alright, this doesn't seem like a theory reference at least, but let's see here. Our experiments approach based on evaluating the correlator between OT and a measurement operator M, which is another Pauli operator on a different qubit. Did they mention that? I mean, that completely changes the thought process if it's on a different qubit. Because if this Z is on a different qubit, then these things commute. And okay, well, let's see what's going on here. Where this denotes expectation value over a particular quantum state. Consider position and momentum operators in a quantum system. We can define the out-of-time correlator as out-of-time order correlator as the expectation value of the commutator of x at time t and p of 0 squared. Taking the naive semi-classical limit, we would be able to replace the commutator by the Poisson bracket for classical chaotic system with Lyapunov exponent lambda. We have this thing as lambda t because the sensitivity to initial conditions. Thus the out-of-time order correlator should grow h bar to lambda t. We can read off the Lyapunov exponent from it. Lyapunov. Yeah, it's not too useful. But these guys are definitely talking about, so these things commute when t is not 0. But I don't know if they're. Is this the thermal average? I'm not sure what a thermal average means in this sense. Average in quantum mechanics. Okay. So they mean the eigenvalue, if this is what they mean the eigenvalue, but a weighted average of the eigenvalue with respect to this Boltzmann distribution. This is a really weird formula, though. I don't know what a Lyapunov exponent is, although I've seen these before. Alright. Anyway, so an MBL-DTC phase, A0 nearly coincides with the envelope, suggesting that the decay of the latter is primarily induced by T-clearance. The reference signal A0 may be used to normalize A and reveal its ideal behavior. A over A0, shown in the upper bands, decays rapidly for G equals 0.6, but retains near maximal amplitudes for G equals 9 and 7. Similar contrast between two phases is seen in the error-mitigated autocorrelators, A over A0 for all qubits. Figure 2D. This is just saying that they see this exact same thing on all the qubits. Okay. Now to systematic analysis of next requirement necessary to establish MBLDCC, namely the presence of eigenstate order across the entire spectrum, which in turn implies that subharmonic response should not be strongly affected by choice of initial states. All right, I think I am going to call it here just around 9 o'clock. So to anybody who was watching, thanks a lot, really appreciate it. And I will be on again tomorrow night. Gonna try to do from 7 to 8. So thanks a lot, and I'll see you next time.